You glance at a wall clock and the second hand seems to hold still for a beat too long. It sits there, frozen longer than any second should last, and then it jerks forward like nothing happened. That frozen stretch in the world is not the clock, and it is not your eye. It is your brain editing the past in real time. You have felt it 100 times in classrooms, in kitchens, on your phone, and each time the world stutters and you move on without asking why. The illusion has a scientific name, a discoverer, and a landmark experiment, and together they reveal that the timeline you experience is not recorded. It is built. By the end of this video, you will know why the clock freezes, and why the answer reaches far beyond clocks, into everything you remember, everything you decide, and whatever you mean by the word now. The effect was given a proper name decades after it was first noticed. A British physicist named Donald Mackay described it in the late 1950s. He asked people to look directly at a clock instead of glancing at it, and the strange thing disappeared. That was the clue. The freeze only happens when your eyes jump toward the clock. In vision science, those jumps are called saccades. Mackay noticed that the first tick after a saccade seemed to stretch out, and he suspected the brain was covering up something. But measuring an illusion of time is difficult. A duration 100 milliseconds long feels different to everyone, and nobody can describe it reliably. So the idea sat mostly dormant for 40 years. The name that stuck, chronostasis, from the Greek for time standing still, arrived only after the effect could be measured in a controlled laboratory setting. Before there were laboratories, there were only anecdotes. People with pocket watches knew the trick long before it had a name. If you flipped open the watch and looked down, the second hand appeared to hesitate as if embarrassed to be watched. Writers joked about lazy clocks. No one treated it as a mystery of perception, because the obsession with objective time was new, and the clock was trusted more than the senses. Then the measurement of eye movements became possible. Early researchers found that a saccade is fast, 20 to 50 milliseconds, yet almost nothing is seen during it. Your eyes sprint from one point to another, and for that entire sprint, your visual system stops delivering detail. So the question became, where does the missing time go? Mackay had an intuition. The missing time is not discarded. It is filled, covered over, stitched shut, so silently that you never feel the seam. The deadlock broke in 2001. A team of researchers led by Keelan Yarrow at University College London designed a clean test. They showed people a set of digits on a screen, ticking much like a second hand. The task forced the eye to make a saccade to a target just before a change in the display. After the eye landed, the first interval between changes was compared to intervals the same person experienced without moving the eyes. The result was consistent. The first interval after a saccade felt longer by roughly the duration of the eye movement itself. A saccade of 40 milliseconds stretched the first tick by an extra 40 milliseconds. The numbers matched. The brain was not distorting the clock. It was inserting the time it lost during the saccade into the first thing it could anchor to, the first visible event after the eyes landed. Published in Nature, the study gave chronostasis its modern definition and its experimental foundation. The foundation of the illusion is a hidden gap in your vision. Every saccade lands inside a window of suppression. As your eye muscle accelerates, your brain turns down the flow of visual information from the retina. If it did not, the world would smear into a violent blur at every glance. The suppression is so effective that, under ordinary conditions, you never notice a blackout. You open your eyes, you move them, and the world appears smooth and continuous. But smoothness is a lie. Between one glance and the next, there is no image at all. To make the story seamless, the brain takes the first clear image it can use after the eye stops moving and stamps it with an earlier time. The result is what philosophers call an antedated percept. You experience something before the moment your nervous system actually received it. The clock's first tick seems long because the brain dragged a normal tick backwards to cover dead air. Think carefully about what backdating means. It means your conscious timeline is a patchwork of pieces from different physical moments. Take reading a book. Your eyes jump from word group to word group, and during each jump the text is invisible. The page you perceive is not the page as it arrives. It is a composite, assembled from stable snapshots taken after each jump and assigned slightly false times. The stopped clock is just one visible case. The same stitching happens constantly. You never catch the world mid-glance because your brain has never once shown you a mid-glance frame. It simply edits it out of the record and hands you a clean version of what happened, complete with a timestamp that was never real. That is why the clock can seem to hold still for a beat far longer than it should. The brain is not failing. It is doing exactly the job it evolved for, producing one calm, continuous story with no gaps and no blur. If time can be stretched by eye movements, then time must be elastic in other ways. And it is. In the 2000s, the neuroscientist David Eagleman tested a famous perceptual trick called the oddball effect. You show people a sequence of identical shapes on a screen. Then you insert one shape that is different, say a blue square among gray squares. People report that the odd shape stays on screen noticeably longer than the others, even though its duration is identical. The brain spends more processing power on novelty, and more processing means a longer felt duration. So the same rule appears twice, once in the eyes and once in attention. Time becomes dilated where the brain does heavy work. The clock freezes not because the second hand moved slowly, but because your brain spent extra effort stitching the moment together. A surprising detail, an unexpected event, a new environment, all of them stretch time in the same way. There is another line of evidence that the timeline is built backwards. It is called the flash lag effect. Put a moving object and a stationary flash side by side in the same spot, and ask people where the moving object was when the flash appeared. Everyone reports that the moving object sits slightly ahead of the flash. The brain delays the movement signal, aligns it with the flash, and builds the scene after the fact. The present you perceive is already a sketch of the recent past. Even your sense of the world being stable depends on this same stitching. As your eye sweeps a room, your brain compresses the gaps and stretches the new views into an even progression. Without the illusion, every glance would feel like a tiny jump cut. The miracle is not that clocks sometimes freeze. The miracle is that you do not experience every moment as a small, painful discontinuity. The illusion has boundaries, and those boundaries are informative. It relies on discrete events you can anchor to. A wall clock with a hand that sweeps smoothly does not trigger the effect as strongly. The brain needs a clear marker, the tick, to pin the stretch time to. A long saccade, one that crosses most of your field of view, also changes the picture. The illusion grows with saccade duration up to a point, then it stops growing. Some researchers suspect the brain simply cannot backdate beyond a certain window, roughly 100 milliseconds. Beyond that, the patchwork falls apart. People who track a moving object with smooth pursuit eye movements never see the freeze, because there is no gap to conceal. And people who make many small saccades, like a musician reading a score, rarely notice the effect at all. The illusion thrives on inattention. It is a quiet background operation that only reveals itself when you catch it red-handed and isolate 1 second from the flow. Modern neuroscience frames these findings inside a larger theory called predictive processing. The brain is not a camera that records, and it is not a tape player that replays. It is a prediction engine. It constantly generates a forecast of what the senses are about to deliver, and it mostly compares signals against that forecast to save energy. The stopped clock illusion becomes one more piece of evidence that experience is mostly forecast plus a small correction. Your brain predicted what the clock would look like after your eye landed, and it backdated that prediction into the gap created by the saccade. When the prediction is right, the world feels smooth. When the prediction fails, you get a surprise, and the surprise stretches time because the brain must do new work. This is why the first tick of a clock after a glance feels so long. It is not a tick. It is a tiny reconstruction, and reconstruction costs time. The implications extend beyond clocks into the texture of your whole day. Memory and duration are built by the same kind of stitching. A week of routine collapses because there is nothing new to anchor the timeline. A vacation expands in memory because every unfamiliar street and meal forces the brain to do heavy editing work. The same logic explains why the first bite of a meal tastes longer than the last, and why returning home from a familiar commute feels like teleportation. Your brain edits out the predictable, and the edit is so thorough that the events themselves seem to have never happened. The frozen clock is the small, visible corner of this machinery. In most of life, you never see the stitch at all. The numbers on a window tick past, the days blur, and you only notice time when something unexpected forces your brain to build a new frame. There is a practical edge to all this. The illusion measurably distorts your sense of timing in sports, in driving, and in conversation. When you glance at a dashboard or a phone screen, your estimate of how long the glance took is stretched by the saccade. The distortion is small, tens of milliseconds, but it accumulates across millions of glances. More interesting is what you can do with the knowledge. You cannot stop your eyes from freezing a clock. But you can learn that the frozen moment is a sign of your brain doing expensive work. You can use that as a reliable marker, a signal that this particular instant mattered enough that your brain had to rebuild it. The effect also warns against trusting your memory of durations. The stories you tell about past time are not recordings. They are reconstructions, edited for usefulness, not accuracy. That is not a flaw. It is the system working as designed. Here is the deepest consequence. If visual time is backdated, then your conscious present is always slightly behind the physical world. The now you experience ended some time before it happened. A century of physics already told you that light takes time to reach your eyes, so the world you see is always the recent past. The stopped clock adds a second layer. Your brain delays events further, reassigns their times, and hands you a story it has already improved. This means the sense of immediacy you feel at every moment, the certainty that this is happening right now, is a construction. It is a very good construction. It predicted your world accurately enough for you to catch a ball, avoid a car, and read a sentence. But it is still a construction. You have never experienced the raw present. You have only experienced your brain's polished version of it, delivered a fraction of a second late, and stamped with a false label. So the second hand on that wall clock was never frozen. Your brain froze it, stretched it, and stitched the gap shut before you had a chance to ask what happened. The clock was telling perfect time. The mistake was yours, in the same way a misremembered melody is yours, or a dream that felt like waking is yours. You are the editor of your own timeline, and the stopped clock is the one moment when the editing brush slips into view. Next time you glance at a clock and catch it holding still, you will know what you are seeing. You are seeing your brain at work. And if the present turns out to be a carefully assembled story told a little after the fact, then the only question worth carrying into the rest of your day is simple. Who is the story for, and how much of it will you bother to write yourself?